Hi, I'm Bhargav and I'm going to talk about a super-quadratic lower bound for depth for arithmetic circuits. This is joint work with Nikhil Gupta and Chandan Saha. So here is the outline for the talk. First, I'll establish some preliminaries about algebraic complexity theory. Then I'll motivate the problem of studying lower bounds for depth for circuits and state our result. After that, I'll talk about some key ideas used to prove our result. And finally, I'll conclude by mentioning some open problems. In algebraic complexity theory, arithmetic circuits are a natural model of computation. An arithmetic circuit is a directed acyclic graph whose nodes are called gates and whose edges are called wires. All gates with n degree 0 are called input gates and are labeled by either a variable or a field element. On the other hand, all other gates are labeled by either a plus symbol, so they are sum gates, or are labeled by a multiplication symbol, so they are product gates. All wires or edges of an arithmetic circuit can be labeled by field elements, and all gates with out degree 0 are called output gates. An arithmetic circuit computes a polynomial in a natural way. For example, this circuit computes the polynomial 3x squared plus 4xy plus y squared. There are two complexity measures associated with an arithmetic circuit, its size and its depth. The size of an arithmetic circuit is equal to the number of edges in it, and the depth of a circuit is equal to the length of the longest path from any input gate to any output gate in the circuit. Now let me talk about algebraic complexity classes VP and VNP. Just as in Boolean complexity theory, we have classes P and NP. In algebraic complexity theory, we have classes VP and VNP. VP is the class of all polynomial families Fn, such that the number of variables in Fn and the degree of Fn are a polynomial in n, and Fn can be computed by a polynomial-sized arithmetic circuit. An example of a polynomial family in VP is the determinant polynomial family. Here DETN denotes the determinant of an n cross n symbolic matrix. On the other hand, roughly speaking, VNP is the class of all polynomial families Fn such that given a monomial, its coefficient in Fn can be computed efficiently. That is, its coefficient can be computed in p to the sharp p. An example of a polynomial family in VNP is a permanent polynomial family. Here, perm n denotes the permanent of an n cross n symbolic matrix. It is easy to see that VP is contained in VNP, and it is conjectured that this containment is strict. Proving this conjecture is a major open problem in algebraic complexity theory. As far as connection between VP and VNP and Boolean complexity classes is concerned, it is known that VP equals to VNP where fields of characteristic 0 or finite fields of prime characteristic implies that P slash poly and NP slash poly, that is, the non-uniform versions of P and NP are equal, assuming the generalized Riemann hypothesis. Here, notice that the problem of showing that VP is not equals to VNP is a lower bound problem, since if we are able to show that there exists a polynomial family in VNP which cannot be computed by any polynomial size circuit, then we would have shown that VP is strictly contained in VNP. So now let me mention some known lower bounds for arithmetic circuits. While ideally we would like to have super polynomial lower bounds for this model, the best known lower bound for arithmetic circuits is omega n log n, which is a superlinear bound. On the other hand, for arithmetic formulas and layered algebraic branching programs or layered ABPs, quadratic lower bounds are known. Arithmetic formulas are arithmetic circuits whose underlying graphs are trees, and layered ABPs are a model of computation that lies somewhere between arithmetic circuits and arithmetic formulas. Now, since it appears to be a difficult problem to prove lower bounds for general arithmetic circuits, one natural thing to do is to somehow restrict the power of a circuit and then prove lower bounds for such restricted models. One such natural restriction is restricting the depth of the circuit. In particular, a lower bound of omega delta times n raised to 1 plus 1 by delta is known for depth delta circuits. As far as arithmetic circuits are concerned, not only are restricted depth circuits a natural subclass, but they are also a very powerful subclass because of what are known as depth reduction results. A depth reduction result is a result of the following form. It says that if a polynomial f in n variables and of degree d can be computed by an arbitrary arithmetic circuit of size s, then it can also be computed by a depth delta circuit of size s prime. Here, s prime is typically greater than or equal to s, but very small compared to n raised to d. So, as far as some particular depth reduction results are concerned, it is known due to the work of Valiant, Skyam, Berkowitz, and Rakov that Vp is equal to Vnc2. Vnc2 is a class of all polynomial families computed by polynomial-sized circuits of depth order log square n. Also, from the works of Agrawal and Vinay, Koiran, Gupta, Kamnath, Kayal, and Saptarshi, and Tavenis, we know of depth reduction results to special classes of depth 3 and depth 4 circuits. So as far as arithmetic circuits are concerned, even depth 3 and depth 4 circuits are very powerful models. A lower bound of n raised to small omega square root d for homogeneous depth 4 circuits, computing a n-variate degree d polynomial in VNP implies Vp is not equals to VNP. In fact, a lower bound of n raised to capital omega square root d is known for a polynomial in VNP as well as for a polynomial in VP due to the works of Kayal, Limaye, Saha, and Srinivasan, and Kumar and Saraf. For depth 3 circuits, a lower bound of n raised to small omega t by tau for depth 3 circuits with bottom fan in tau, computing a n-variate degree d polynomial in VNP implies Vp is not equals to VNP. A lower bound of n raised to capital omega d by tau is known due to the work of Kayal and Saha. Notice that in both of these cases, we are at the very threshold of separation between Vp and VNP, as if we are able to improve the capital omega in either of these lower bound results to a small omega, then we would end up separating Vp and VNP. Both these results use the variance of shifted partials measure introduced by Kayal in 2012. Since techniques using this measure worked so well for special classes of depth 4 and depth 3 circuits, it is natural to wonder if we can improve upon the state of the art for general depth 3 and depth 4 circuit lower bounds using these techniques. In fact, it has been a long-standing open problem to prove a superpolynomial lower bound for general depth 3 arithmetic circuits. The best known lower bound for depth 3 circuits was a quadratic lower bound due to Shipalka and Wigderson, and this stood for a very long time before it was improved to an almost cubic lower bound by Kayal, Saha, and Tavenis in 2016. This work also uses a variant of the shifted partials measure, and so for depth 3 circuits, shifted partials measure indeed gives us better lower bound. But what about depth 4 circuits? Can we prove, say, a super-quadratic lower bound for depth 4 circuits using a variant of the shifted partials measure? In fact, as stated in this decade-old survey by Shipalka and Yehudaov, no super-quadratic lower bounds were known for depth 4 circuits over fields of characteristic other than 2. And this brings me to our result. We prove that over any field of characteristic 0, there exists a family of multilinear polynomials Fn in VNP, where Fn is a polynomial in theta n variables, such that any depth 4 circuit computing Fn has omega tilde n raised to 2.5 many edges and omega tilde n raised to 1.5 many gates. This lower bound continues to hold over fields of large enough characteristic, and to the best of our knowledge, is the first superquadratic lower bound for depth 4 circuits over fields of characteristic other than 2. Now, before I move on to our proof techniques, let me quickly mention some known lower bounds for depth 4 circuits. Due to the work of Pudlak and Raz and Shipalka, a lower bound of omega n times lambda delta n is known for depth delta circuits. Here lambda delta n is a slowly growing function of n. In particular, for delta is equal to 4, that is for depth 4 circuits, lambda 4n is equal to log star n. And so for depth 4 circuits, this lower bound is barely superlinear. Also, due to the work of Shoup and Smolensky, we know a lower bound of omega delta times n raised to 1 plus 1 by delta, and due to the work of Raz, we know a lower bound of n raised to 1 plus omega 1 by delta for depth delta circuits. If we put delta is equal to 4 in these two lower bounds, we get a lower bound of omega n raised to 1.25 for depth 4 circuits. However, it turns out that for the special case of depth 4 circuits, these lower bounds can be optimized and can be made to be equal to roughly order n raised to 1.33. As I have mentioned before, Kayal, Saha, and Tavares recently proved a lower bound of omega tilde n cube on depth 3 circuits, which are a special class of depth 4 circuits. And Sharma in his master's thesis proved a lower bound of omega tilde n raised to 1.5 for depth 4 circuits. Here I would like to remark that all the lower bounds mentioned here, except the almost cubic lower bound for depth 3 circuits by Kayal, and Tavares, are on the number of edges. The almost cubic lower bound for depth 3 circuits due to Kayal, and Tavares also continues to hold for number of gates. Now let me talk about some key ideas that we use to prove our result. Here is a general template for proving arithmetic circuit lower bounds. Let C be an arithmetic circuit for which we want to prove a lower bound. Then the first thing we do is we express C as a sum of T1 to Ts, where Ti's are polynomials which are simple in some sense. For a depth 4 circuit, a Ti is product of sparse polynomials Qi1 to Qim. The next thing we do is that we construct a measure mu, which is subadditive, that is for any polynomials f and g. Mu f plus g is less than or equal to mu f plus mu g. Mu is such that mu ti is less than or equal to a for some small quantity a, and there exists an explicit polynomial f such that mu f is greater than or equal to b for some large quantity b. For the rest of this talk, I'll refer to this explicit polynomial f as a hard polynomial. Now, if the circuit C computes a polynomial f, then mu c has to be equal to mu f, and therefore s is greater than or equal to b by a. If b is large and a is small, then we get a good lower bound on the size of the circuit C. Therefore, our goal is to prove a small or upper bound on mu ti and a large lower bound on mu f. Now let me mention one such measure. It is called the dimension of the projected shifted partials measure, or DPSP measure. It was first introduced in the work of Kayal, Limaye, Saha, and Srinivasan. It has three operations, the first of which is taking partial derivatives with respect to multilinear monomials of degree k. The second operation is shifts, that is multiplications with multilinear monomials of degree L. And the third operation is multilinear projection, that is projecting a polynomial to just its multilinear monomials. It is not too difficult to see that DPSP is a subadditive measure, and the reason I mentioned this measure is because the measure that we use in this work is obtained by augmenting DPSP by adding two extra operations to it. I'll talk about our measure later. For now, let me focus our attention on upper bounding the DPSP measure for an arbitrary depth 4 circuit C. We start off by observing that the proof in the work of Kayal, Limaye, Saha, and Srinivasan is a little more general in the sense that although it proves a lower bound for homogeneous depth 4 circuits, the proof also works for depth 4 circuits C is equal to T1 plus T2 plus T3 up to Ts, where Ti is a product of sparse polynomials Qi1, Qi2 up to Qim, if all monomials in Qij have low support and m is small, that is m is less than or equal to square root d. Here I would like to remark that the use of the DPSP measure forces d to be less than or equal to square root 10. This is a technical condition, and because of this, we can restate the second condition as m being less than or equal to square root n. In the next few slides, I'll talk about how we ensure condition 1 and 2 hold for arbitrary depth 4 circuits. Let me first talk about the first condition. To ensure that the first condition holds for arbitrary depth 4 circuits, we reduce their bottom support. Previous works had this step of reduction of bottom support, and they accomplished this by using random restrictions. In random restrictions, one randomly selects a set of variables and sets them to 0. Notice that since we are setting a few variables to 0, the hard polynomial loses some variables, the hard polynomial loses some monomials, and therefore it takes a hit. To better control the effects of such restrictions on the hard polynomial, we use deterministic restrictions. And I'll talk more about these deterministic restrictions later when I'll talk about the hard polynomial. This takes care of the first condition. Now let me move on to the second condition. Recall that our second condition was that Ti, a product term which is a product of Qi1, Qi2, Qi3 up to Qim, should be such that m is small. Now, using the grouping trick from the work of Kayal, Saha and Tavenis, we are able to handle m roughly equal to n times d. In the grouping trick, what we do is we take a bunch of Qij's and multiply them together to obtain new polynomials Q prime ij's. This reduces the value of m, and so we are able to handle large values of m. Here I would like to recall that the use of the DPSP measure forces d to be less than or equal to square root n, and so we are able to handle m, which is roughly equals to n raised to 1.5. In the work of Kayal, Saha and Tavenis, they were able to handle d equals to theta n because of the use of shifted partials measure. So by using the DPSP measure from the work of Kayal, Limaye, Saha and Srinivasan, and the grouping trick from the work of Kayal, Saha and Tavenis, we get a lower bound of omega tilde n raised to 1.5 on the number of edges of a depth 4 circuit. If we want to obtain the same lower bound for number of gates of a depth 4 circuit, then we need to assume that all sparse polynomials Qi1, Qi2, Qi3 up to Qim are distinct. If this is not the case, then we can use powers of these sparse polynomials and our analysis can still be made to work in this case. Because of this reason, for the rest of the talk, I'll assume that for every product term Ti, this polynomial, the sparse polynomials Qi1, Qi2 up to Qim are distinct. So now let me talk about how we improve the omega tilde n raised to 1.5 lower bound obtained from KLSS and plus KST to a lower bound of omega tilde n raised to 2.5. We do this by using the notion of a heavy gate. We define a heavy gate as follows. A product gate in the second level is said to be heavy if it has omega tilde n raised to 1.5 many distinct sparse polynomials feeding into it. The problem with heavy gates is that the DPSP measure of a heavy gate is large, and so it is difficult to prove a small low upper bound on the measure of a depth 4 circuit which contains a heavy gate. On the other hand, the good news is that if the number of heavy gates is t, then the size of a circuit is already greater than or equal to n raised to 1.5 times t, and this suggests the following natural strategy. If t is large, then we already have a lower bound of n raised to 1.5 times t. Otherwise, if t is small, we can remove all the heavy gates from the circuit and then prove a lower bound on the residual circuit. The next few slides, I'll talk about how we remove heavy gates, but before that, let me just mention that we are able to get a lower bound of omega tilde n raised to 2.5 because we are able to handle n heavy gates without weakening the hard polynomial much. Now let us see how we remove heavy gates. Consider a heavy gate Ti is equal to Qi1, Qi2, Qi3 times Qin, where, as I mentioned before, I'll assume that Qij's are distinct sparse polynomials. Notice that in a depth 3 circuit, Qij's are affine forms, and so in the work of Kayal, Saha and Tavenis, they were able to remove heavy gates by going modulo an ideal generated by affine forms. A natural extension of this idea for the case of depth 4 circuits would be to go modulo an ideal generated by sparse factors. However, the question is, can we do this? Well, maybe we can, but the problem is if we go modulo an ideal generated by arbitrary sparse polynomials, then the quotient ring that we obtain might not be a polynomial ring, and it is not clear how to obtain or define a good measure mu for such a quotient ring. We bypass this problem by staying in a polynomial ring, and the way we do this is as follows. We assume without loss of generality that F is an algebraically closed field, and then we sequentially evaluate one sparse factor of each heavy gate to 0 by setting variables in it to elements in F. An immediate problem with this idea is that what if we set all variables to field elements? In this case, the hard polynomial will become a constant and we won't get any lower bound. The way we deal with this problem is the following. Our goal is to remove as many heavy gates as possible using as few variables as possible. But since we have already restricted the bottom support of the circuit, few monomials is the same as few variables, and so we can afford to get rid of as many heavy gates as possible using as few monomials as possible. Then we reinterpret the goal of removing heavy gates as an instance of the weighted set cover problem. The universe of this instance is a set of all heavy gates, and the collection of subsets of the universe, which we can use to cover the universe, contains one sparse polynomial, contains one set for each sparse polynomial, and this set contains all heavy gates connected to that sparse polynomial. The cost of such a set is equal to the number of monomials in the corresponding sparse polynomial. After this reinterpretation, our goal becomes the following. We want to cover the entire universe using the collection of subsets corresponding to sparse polynomials while incurring as small a cost as possible. Also, this reinterpretation suggests that to get rid of heavy gates, we can use a procedure which is similar to an approximation algorithm for the weighted set cover problem, and this is exactly what we do. The procedure that we use is the following. While there exists a heavy gate, pick a sparse polynomial q, for which the ratio of the number of heavy gates connected to q to the monomials in q is maximum, and evaluate such a sparse polynomial to 0. We're able to show that this procedure kills omega n heavy gates without affecting the hard polynomial a lot. Now let me talk about the hard polynomial. Our hard polynomial is a variant of the Nissan-Wigderson design polynomial denoted NW. The reason we use the Nissan-Wigderson design polynomial is because previous works have shown that PPSP of Nissan-Wigderson is large. So if we can use Nissan-Wigderson as our polynomial, we have a large lower bound and we are done. However, since we are setting some variables to field elements, we might damage a Nissan-Wigderson polynomial, and this might reduce the PPSP measure of the polynomial. We handle this problem by including multiple copies of the Nissan-Wigderson polynomial in our hard polynomial f. In particular, our hard polynomial f is a polynomial in 3 and x and 3 and y variables, and contains one copy of Nissan-Wigderson polynomial for every subset S of 3n of size n, along with a prefix in y variables. The main part of our hard polynomial are these multiple copies of Nissan-Wigderson polynomial, and we use the y variables to stitch these multiple copies together. We are able to show that deterministic restrictions and removing heavy gates use up 2 and many xi yi variable pairs. While implementing deterministic restrictions and removing heavy gates, we ensure that if a variable xi is set to some field element, then the corresponding variable yi is also set to some field element and vice versa. Because of this and our use of deterministic restrictions, we are easily able to show that after we have removed heavy gates from the circuit, the polynomial f computed by the circuit contains one intact copy of a Nissan-Wigderson polynomial along with its corresponding prefix in y variable plus a residual polynomial f prime whose y degree is strictly less than n. So if we are able to remove f prime and the prefix in y variables from the polynomial f and then apply the DPSP measure to it, we would have a large lower bound on the measure of the hard polynomial. The way we do this is by augmenting the DPSP measure by adding 2 extra operations to it. Let me call the measure that we use the DPSP prime measure. It contains all the operations of the DPSP measure, that is, the partial derivatives, shifts, and multilinear projections. However, unlike the DPSP measure, where these 3 operations are carried out with respect to all the variables in f, we only carry out these operations with respect to the x variables and not with respect to the y variables. The first new operation that we introduce only keeps monomials of y degree exactly n. Notice that this operation removes f prime from the polynomial f. The second operation sets all y variables to 1, and thus this operation removes the prefix in y variables from the hard polynomial f. And after these 2 operations have been applied, we are only left with one intact copy of the Nissan-Wigderson polynomial. Because of this, we are able to show that dPSP prime of f is equal to dPSP of Nissan-Wilderson excess, which is large as the size of S is n. So we have a large lower bound on the measure of a hard polynomial, and we are done. Now let me conclude by quickly recapping all the key ideas that we used to prove our result and then mentioning some open problems. The ideas that we use in our proof are the following. We use deterministic restrictions to reduce the bottom support of a depth first circuit. The reason we do this is to better control the effects of these restrictions on a hard polynomial. We interpret the problem of removing heavy gates from a circuit as an instance of the weighted set cover problem and remove n heavy gates. We use the grouping trick from the work of Kayal, Saha, and Tavenes to group the sparse factors together while analyzing the dPSP measure of a term. Because of this trick, we are able to handle product terms with n raised to 1.5 many distinct sparse polynomials feeding into them. And because of this grouping trick and our ability to remove n heavy gates, we are able to get a lower bound of n raised to 2.5. Lastly, we include multiple copies of the Nissan-Wilderson polynomial in our hard polynomial f, and we augment the dPSP measure to mitigate the effects of deterministic restrictions and removing heavy gates on a hard polynomial. Now let me quickly mention some interesting open problems. It would be interesting to prove a super-quadratic lower bound on the number of gates of a depth 4 circuit. The almost cubic lower bound for depth 3 circuits from the work of Kayal, Saha, and Tavenes is also on the number of gates. Another interesting problem is to improve this lower bound, this super-quadratic lower bound to an almost quadratic lower bound. We would be able to do this if we can tolerate t, the degree of the polynomial, equals to theta n. The reason we are not able to do this in our work is, as I mentioned before, our use of the dPSP measure. Another interesting problem is to prove a super-quadratic lower bound for a polynomial in VP. An almost quadratic lower bound for depth 3 circuits is known for polynomials computed by small depth 5 circuits. Also, proving lower bounds for the polynomial IMM2n will be interesting. It follows from ideas in the work of Chen and Tell that if IMM2n, that is the multiplication of 2 cross 2, the multiplication of n many 2 cross 2 matrices whose entries are distinct variables, can be computed by a depth delta 0 circuit of size n raised to k, then it can also be computed by a depth delta circuit of size order delta divided by delta 0 times n raised to 1 plus exponential minus delta divided by delta 0 k. Because of this, if we are able to prove a lower bound of omega delta times n raised to 1 plus 1 by delta for a depth delta circuit computing IMM2n, we would have shown a super polynomial lower bound for constant depth circuits. In fact, recall that a lower bound of omega delta times n raised to 1 plus 1 by delta is already known for depth delta circuits due to the work of Shoup and Smolensky. If we are able to put the same lower bound for IMM2n, we would have a fantastic result. That is a super polynomial lower bound for constant depth circuits. Even for depth 5 circuits, we have the following observation. If we are able to prove a quadratic lower bound on the number of gates of a depth 5 circuit, computing IMM2n, then we would have shown a supercubic lower bound on the size of depth 3 circuits, and this would be an improvement on the almost cubic lower bound for depth 3 circuits from the work of Kayal, Saha, and Tavenes. Thank you.